Yeah, the next chapter is I want to show how to work with signal block diagrams if the electronic circuit contains OpAmps. Yeah, OpAmps with SBDs. You will see that is rather simple. So I think a short repetition is necessary. What is an OpAmp? An OpAmp, the symbol for an OpAmp is a triangle. Triangle here with an output signal, and an OpAmp has two input lines, two input pins, a positive input pin and a negative input pin. And the voltage between these both pins is a differential voltage. This is amplified with a gain V to the output lines. So there's an output voltage, say O, and the gain, the equation we use for this in the first approximation is very simple. Ignoring currents, input currents, ignoring noise and so on, is OpAmp is a differential amplifier. U sub O is differential gain times input differential voltage. So with this gain, V, the input voltage is multiplied and sent to the output voltage. And operational amplifier has not really a ground pin. The voltage is measured in respect to ground, but the IC, operational amplifier, has no ground pin. I think I should show you the one example for an operational amplifier. If you, for example, look in Google for the MU-A741, that is a really standard operational amplifier existing since 35 years. I think the eldest still existing operational amplifier I still know. The MU-A741 is, for example, in a housing an 8-pit dual inline package. So there are 8 pins. You see here the main pins is a negative input pin, positive input pin, and the output pin, but no ground pin. If you look here, we have no ground. This is not ground, not really a ground. We have a positive voltage input pin 7 and a negative voltage input pin 4. If this is positive and this is negative, the output voltage can change between these both voltages. If this is really ground, then the output could not be negative, and the normal operating of an operational amplifier is a bidirectional output voltage. So this is normally plus 15 volt, this is negative 15 volt, and there's really not a ground pin. We ignore the offset, we ignore the pin 8 is not connected. So there is offset possibility, but at this time we ignore any offset voltage. So where we can get the ground pin, very simple, by using a double power supply with the following grounding. I go back now to the OneNote. The typical behavior is, the typical connection is, we have here a positive input pin, negative input pin, output pin. That are the 3 pins really existing, and then we have a plus VCC and a negative VCC voltage. And in our application, then we need 2 voltage sources, one for the negative one and one for the positive one, and the double power supply is grounded in the middle. Now this is plus 15 volt, this is plus 15 volt, so that this is a negative 15 volt voltage, and the connection between 2 power supplies is a real ground. So this 2 batteries or 2 power supplies delivers my ground pin. So we can say this is a virtual ground in my system. Okay, so far. Back to the dynamical operation. output voltage is differential gain times input differential voltage. We work with 3 approximations for V. Approximations for V. The first one is very simple. The differential gain is normally very large, and we assume that this voltage gain is infinity. That means if there is an input voltage and the gain is infinity, output is also infinity. That is not the way we want to work, so we can say if the output voltage is within these both voltages, that follows automatically to the fact that the input differential voltage is nearly 0, because maybe this is 10 volt, 10 divided, then UD is 10 volt divided by infinity, and this is 0. So this means input UD is round about 0. But of course this is not always allowed, because the real voltage gain is not infinity. So sometimes we say this is V is a large value but constant, and in the data sheet you can look for what the supplier of this IC guarantees. For example, the UA741 guarantees 20,000 for MU-A741. So depending on the type of the IC, you can look into the data sheet and look for the guaranteed DC gain. But a third approximation is necessary if you want to have frequency behavior of this, and the frequency means if the frequency goes higher and higher, then the gain goes down. The operation amplifier behaves like low-pass filters, and this is expressed by a transfer function of my V, which is the DC gain divided by 1 plus PT. And the DC gain is similar to approximation number 2, and the time constant depends on the data sheet value, depends on the type of the operational amplifier. If we look into the Bode plot of this V, if we say V magnitude in dB expressed in dB, then we can say, okay, for low frequencies we have V0 in dB, then there is a corner frequency at 1/T, and then we have a gradient down to 0 dB. So there is a unity gain frequency, which is, if you calculate this, we can say this is exactly at a value which is V0 divided by T. That is a gain bandwidth product. That is a frequency F. F is depending on DC gain and the time constant of the signal. So if this is F, then of course I have to write divided by 2 pi. 1/T is the omega corner frequency. We will discuss similar Bode plots later in this lecture. Wait for this. In chapter 3 we discussed more detail how to set up a Bode plot of circuits. Here this is a data sheet value of an operation amplifier, and we can also call this a gain bandwidth product. This value is a gain bandwidth product. Okay, so far for our signal block diagram we just work with this equation. That's all. Let's make an example. Very simple circuit. is the following. Example. A very simple circuit is operational amplifier without any additional component. Just what we do is we connect the ground line with input and output voltage. Then we connect our input voltage with the positive input of the pin. This is U1. And then what we do is the negative input pin is connected to my output pin, and then I have an output voltage U2. And the question is, what is this for an amplifier? Maybe you know this typical amplifier with operational amplifier is, typical circuit is if the output is directly connected to the negative input pin, this is a unity gain amplifier. Unity gain amplifier. In other words, the gain is 1, but the input current is very small, it's nearly 0. So what we can see is we have here, we can have a voltage source which is not not loaded, and this output voltage is has the same sign than U1, but here you can of course say this current could be around about 20 milliampere max or so. Max. So here you can get current and the source is not loaded, so we can also say this is an isolation amplifier. This is another word. Isolation amplifier. Okay, signal block diagram. SBD is used. SBD. We need equations. First equation is the operational amplifier equation. U2 is V times UD. So we have an internal unknown parameter, that is UD. So we need one additional equation. The equation should contain U1, and we go into a voltage loop. U1 is UD, so U1 is, I follow the loop, UD plus U2 is UD plus U2. Okay, in this circuit the only possibility is that this is the input voltage and this is the output voltage, so my signal block diagram is very simple, defined with a U1 input and a U2 output. The first equation can easily be drawn. This is just a block with input UD. It's operational amplifier with gain V. U2 is the transfer function times UD, and V is then the transfer function. Yeah, UD times V gives U2. So the first equation is just simple this block. And now we need an equation for UD as an output. If we look for this equation, this is very simple. UD is U1 minus U2. So we have a summing point. Output is UD. And the summing point has two inputs, U1 and U2. U1 is here. U2 is here. And the only thing is what we have to add is a minus sign here for this part. So the simple isolation amplifier is expressed in a signal block diagram with this circuit, and here we can calculate now the behavior of this circuit with any approximation of V. Either V is infinity, or V is large constant, or V has this transfer function independent of this. The signal block diagram in any way can now be used to calculate the overall behavior of this unity gain amplifier. Yeah, that is one version, first version. Just for training, I add a second version. second version. Again, here U2 is the output, U1 is the input, and now I start with the second equation. Yeah, U2 backwards, second equation. If I solve this equation to U2, you see U2 is summing point result. U2 is U1 minus UD. I bring UD on the left side with the minus sign. Is U1 minus UD. Minus UD. For a minus sign, we need now the UD value, and here I solve this for UD. Very simple, UD is 1 over V times U2. Very simple. I have a block with 1 over V. Input is U2. So, this is one version, this is the second version. This is the first version, this is the second version of the signal block diagram of an operational amplifier circuit where the output is directly connected to the negative input. Okay, I give you now a training task. Training task where you can send me your results. You should train setting up block diagrams with the next circuit. First I show you the circuit. Training example. You should do this, and I want to see your results you can upload your result as PDF into the Moodle course. I have to prepare the uploading feature, but I think I want to see this from everybody of you. The circuit is first an operational amplifier circuit with two resistors, two impedances. I call this impedance Z1, and there is a second impedance Z2. This could be any combination of R and for resistances, capacities, or inductivities, giving a complete impedance. The feedback must be connected to the negative input. The positive input is grounded. And that's all. We have now the circuit. The virtual ground is also connected. Yeah, it's the ground for the two power supplies. Here we have a U1 input, and here we have a U2 output. And of course we have here an input current. This current is 0, okay, but here could be a current, because if this voltage is 0, U1 is completely the voltage drop over Z1. So this is an input current, I, which is not 0. But if this current is 0, the input current of the operational amplifier is 0, the gain is again V, then we know the current through Z2 is also I. So, and to set up the signal block diagram, we need some equations, because we have, sorry, mistake. Note that the arrow of the operational amplifier input voltage goes always from plus to minus. Here you see the negative feedback must be negative, goes to the negative input, so the arrow goes from plus to minus is in this direction. This is UD. And we have equations. How many equations we need? First, U1 is input, no other chance. U2 is output. We need at least one equation for connection U2 with U1, and we have an unknown is the unknown is UD is unknown, and I is unknown. So we need at least 3 equations. Yeah, one for this, and for each additional unknown in additional equation. So we need 3 equations. This training example should train setting up the signal block diagram, not setting up equations. So we do these equations now together. First equation is OpAmp equation. No question. We use an OpAmp, and we can directly write down the OpAmp equation. U2 is the output of the operation amplifier. This one is V times differential input voltage. So this is again always the operational amplifier equation. So this complex semiconductor chip is just this simple equation. All other things are neglected. Second equation could be this voltage input loop. Loop 1 is U1 is I times Z1. I times Z1 could also be complex values, no problem. To have AC behavior with complex numbers. Later we will see how we can work with this. If you're not familiar with this, it's easy to show how I want to do this. I times Z1 is the voltage over Z1 minus UD is 0, minus UD. So U1 is this voltage minus this voltage. That's the loop number 1. And the loop number 2 is the output loop. There is a third loop, of course, the overall loop, but you know, in a system with two loops, I have 3 loop equations, but only 2 are valid. So I take the outside loop, just I follow this line and see UD, UD plus I times Z2, I times Z2 plus U2 is 0, plus U2 is 0. So these are the equations, the 3 equations. We know this is input, this is output, and now your task set up SBD. I want to see your signal block diagram with these 3 equations. I think that is not so difficult. Yeah, U1 input, U2 is output. With these 3 equations, you should do this job, I think, 5 minutes. And then make a photo from your working handwriting. I want to see handwriting, yeah? I want to see your handwriting job. Make a photo or a scan and send me the picture in the following way. Upload in Moodle course. I install this now. Upload in Moodle. I make an upload application for training example number 1. Okay. Yeah, in the Moodle course Control System 1, you can find this upload possibility behind after the videos here in upload training example 1. Here, if you open this, you can it's my my page. You can upload your tasks. Yeah, so I think this is that what I expect that you do after looking video CS1 8, number 8. Thank you.